Thank you. Happy post-lunch afternoon session, everyone. I'm going to continue the theme of talking about hurricanes today. And unlike this AI-generated image of a hurricane, the model I'm going to be talking about today actually knows which direction the wind should flow about a hurricane. So we're off to a good start. My name is Michael. I'm an assistant professor at the University of Miami, and I have a problem. I know a lot of you are probably saying, Michael, tell us something we don't know. What I mean is, I'm very interested in the problem of tropical cyclone rapid intensification. And I'm sure everyone in this room is familiar with why we care about this topic, namely that tropical cyclone damages tend to scale with the intensity of the storm. So storms that undergo rapid intensification quickly become more dangerous. But also compounding this issue, unfortunately, rapid intensification events are pretty poorly predicted. And that's illustrated in this figure you see here, where we have the official National Hurricane Center intensity forecast error, average over a 5-year period, as a function of lead time here on the x-axis. For all intensity change events in the black line, and specifically rapid intensification events in the gray line. And so you can see that these RI events are associated with forecast errors that are 2 to 4 times larger, regardless of lead time. And an example of this kind of compounded problem that rapid intensification poses was nicely illustrated by the case of Otis, although Tom talked about this earlier in the week, so I don't need to labor it too much. But I just want to illustrate this case. On the left, you see an infrared satellite snapshot of Otis when it was a tropical storm at this time, had maximum sustained winds of 45 knots. And the official Hurricane Center forecast called for Otis to slowly intensify over the next 24 hours or so to become a 55 knot or moderate tropical storm system. However, Otis underwent a period of extreme rapid intensification and actually intensified to a Category 5 hurricane of maximum winds of 145 knots. And not only did it undergo this period of rapid intensification, reach Category 5 intensity, it did so right before landfall. And not only did it do it right before landfall, it did it making landfall in the Acapulco area of Mexico, which is very heavily populated, and caused catastrophic damage, as you can see from these figures here that I stole from the National Hurricane Center Tropical Cyclone Report. So you could see really extreme wind damage in these high-rise structures right along the coast. And there's also torrential rainfall that led to catastrophic landslides. So these rapid intensification events are very problematic, and it's not just Hurricane Otis. The Hurricane Center came out with a report, I believe the end of last year, where there's a figure from there where they show the last 4 Category 5 landfalls in the Western Hemisphere. So you can see Michael on the top left, Hurricane Dorian on the top right, Otis on the bottom left, and last year we had another one, Hurricane Melissa in Jamaica. And you can see that for all of these cases, the forecast intensity was underestimated. And so the official forecast is by the gray lines is a function of time along the x-axis here. And you can see that Otis in the bottom left was particularly poorly forecast. And it's interesting that Otis was the only one of these systems that didn't have aircraft reconnaissance in sampling the center of the storm, the kinematic structure, until it already attained hurricane intensity. And at this time, then the Hurricane Center forecast caught on, in part because it was already undergoing rapid intensification, but also the computer model guidance kind of picked up on this better as well, potentially aided by the fact that we had better in situ observations of the kinematic structure. So it's not just Otis, rapid intensification is a problem. So why do we care about the 3-dimensional wind field then, the title of this talk we're going to be talking about today? Well, it turns out that knowledge of the vortex structure can aid our situational awareness of the likelihood for a system to undergo rapid intensification. So I have a figure from a paper here that came out last year that I led, where we try to explore whether or not rapid intensification is associated with unique vortex characteristics. And so we used airborne Doppler radar analyses, compare the vortex structures of rapidly intensifying systems, shown in the orange bars here, to slowly intensifying or non-intensifying systems. And we found that these RI systems are associated with significantly taller vortices and significantly more narrow vortices than both slowly intensifying or non-intensifying systems. And the right panel is just a fancy term we use to combine the height and width metrics called the vortex favorability. And you can see there's pretty clear, there's overlap, but there's definitely this preference for RI systems to have unique vortex structures. So how do we observe the 3-dimensional wind field? Right now, the best tool we have, in my opinion, I'm a little biased, is the tail Doppler radar. But I think to kind of illustrate that, I have this figure from a paper that Altuak led a couple years ago. This is a case of Hurricane Maria, where you're looking at observational coverage from various platforms. On the left is a horizontal plan view with respect to the storm center of Hurricane Maria, and the right is a radial height cross-section. So you have atmospheric motion vectors, satellite derived in the blue dots. You can see the flight level observations in the purple dots. They release dropsondes that are shown in the green dots. In this case, we even had an uncrewed aerial system or a drone out there denoted by the red dots. We called it Coyote at that time. But none of these platforms really compares to the amount of observational data you get from the tail operator system shown in the gray dots here. And you see high density in the radial plot, or the plan view plot on the left, but this extends throughout a great depth of the troposphere. And so this is an incredibly valuable system. And these tail Doppler radar observations are transmitted to the Hurricane Center in real time, so forecasters can have improved situational awareness in making these forecasts. And they're also assimilated into NOAA's operational high-resolution hurricane models called HAFS, or the Hurricane Analysis Forecast System. And recent work has come out that's shown that assimilating these tail Doppler radar observations improves forecast skill of these hurricane models by 20 to 40%, or at least in a data denial experiment done for the 2023 hurricane season. Efforts led by AOML. Yeah?
The idea with the drone is that it flies in areas where humans would be too dangerous to fly, or like have more drones?
100% right, yes. So they released the drone from the P3 out of like the dropzone chute beneath, and it can sample the boundary layer where it's not really safe for crewed systems to observe. And the nice part about the drones too is it's getting more than just the kinematic observations, you're also getting thermodynamic observations too. So it's kind of in some ways like a directable dropsonde.
And can it survive, or is it just a one-off?
It eventually will splash in the surface and then it's done. They currently don't have systems that they recover yet. Yes?
The plots on the previous slide, were those vortex structures prior to RI?
So this is a good question. This is, for all the analyses we have, we're treating this at t equals 0, and we're simply interested, what is the future intensity 12 hours from now? So some of those RI storms had already been undergoing RI previously. So it's unclear to what extent these unique vortex characteristics emerge prior to the onset of rapid intensification. That's one of the motivations for developing this model. So thanks for that question. Anything else? Okay. So I illustrated before, I hope that tail Doppler radar observations are very useful. What do these look like? So I have an animation here for the case of Hurricane Dorian from 2019. What you see in the left panel here is a plan view at a height of 2 kilometers of horizontal wind speed from the tail Doppler radar shown in the color shading overlaid on infrared brightness temperatures. And the right is a vertical cross section taken along the flight track here. And so you can see we get observations about outward to 50 kilometers on either side of the flight tracks. We're not totally resolving the vortex structure, but they remedy this by taking different angles through the center of the storm to try and maximize data coverage. And we get observations throughout basically the entirety of the troposphere. But data is limited to having sufficient hydrometeors. We're not getting observations where there's not hydrometeors present. I mean, luckily hurricanes tend to have a lot of rain, so that works out well. But you don't get anything outside of the swath, and sometimes the QC and other issues can create large data gaps. So there are some limitations. Another limitation, in addition just to the nature of the TDR system, is that we really only routinely have tail Doppler radar observations in this part of the world. And as we all know, TCs occur in multiple basins, and so we don't really have real-time awareness of vortex structure, three-dimensional vortex structure in these other parts of the basin other than going through various data assimilation methods. We don't have direct observations. And even in this area outlined in magenta, where we do have routine reconnaissance observations, there's often large temporal gaps between we have no aircraft sampling a storm, and there's also these spatial gaps I talked about. So is there a way, right, we see that these observations are very helpful in allowing us to diagnose intensity change, rapid intensification, but is there a way we can maybe fill in these data gaps? And so what I'm proposing to do, what I've started to do is use machine learning to create synthetic tail Doppler radar analyses. So we don't always have TDR observations, but we do always have geostationary satellite observations, namely infrared brightness temperatures. And so here I'm going to be using machine learning to act as essentially a virtual hurricane hunter, to creating estimates of three-dimensional kinematic structure using these inputs and inputs that are consistently available in a real-time setting. So the idea here is, right, we have satellite observations, we can train this machine learning model, it's going to spit out some synthetic analysis of the three-dimensional vortex structure. And so because I'm only using inputs that are available in a real-time setting from geostationary satellite, I'm not using, for example, low Earth orbiting satellite observations or other derived products that are not consistently available. This method is going to allow us to theoretically enable real-time estimates of three-dimensional tropical cyclone structure anywhere in the world, basically every time we get a new infrared satellite snapshot. So, oh yes?
This is a silly question. It shows how little I know about remote sensing. So from the satellite, we cannot get any information about like akin to a Doppler radar, like a wings and things like that, just our.
So there are methods to estimate the surface wind, and through synthetic aperture radar, you can get some estimates of like profiles in the low levels, but there's not really a way that I'm aware of at this time to get consistent high-resolution estimates of the vortex structure. You get some atmospheric motion vectors, but that's kind of seeing the height of the cloud and things like that, but it's really difficult to peer underneath the cirrus canopy of a hurricane. Yes?
Like does HAFS just not assimilate GOES? Is it they're using that kind of latent heating trick for the preset field that they get from radar? Is that how that works?
Are you saying how does HAFS initialize their vortex?
Yeah, how do they use the Doppler, the tail Doppler radar?
Oh, so they're simulating that in addition to other platforms like atmospheric motion vectors and things like that. And they go, I'm not super familiar with their data simulation scheme, but I know that they're thinning like the raw radials, and then that's being ingested into creating this initialized vortex. Does that answer your question?
Yeah, I mean, it's just like if you could get it from GOES, they could just assimilate GOES data directly into their system, but it could be that it's just harder to do that. I know some of the convective models do struggle with assimilating geostationary observations or visual data.
Well, they are assimilating like the radiances, but so is your question, if they're assimilating the radiances, how is this providing new information? Yes. That's something I'm actually working on testing, see if that's the case. I suspect it is.
Because sometimes the DA methods just don't do well with the GOES, but they do well with the radar, so it could be that also.
And HAFS does have, should I say this, an interesting vortex initialization process, where they just kind of start from like a bogus vortex when it's not a cycled run, and they kind of assume that the vortex is vertically aligned among other things, and then eventually gets nudged towards a realistic state. But I think there's a way we can maybe have a better starting point.
Oh, okay, because they're not just running it every hour.
They're running every 6 hours, and they do cycle it once it gets above a certain intensity, but for weaker storms or initial runs, it's not cycled yet. Okay, thanks for the questions. So you say, okay, why are we using infrared brightness temperatures? How is that going to be related to kinematic structure of the storm? Well, it turns out from way back in the Dvorak technique, 1973, and since then, we routinely use information taken from the infrared brightness temperature field to infer the intensity of a hurricane. I guess I'm curious, how many of you are familiar with the Dvorak technique? A few of you, okay. So the idea is basically, based upon the spatial pattern of the convective field from infrared brightness temperatures, the curvature of bands, how wide is the central dense overcast, how cold are the cloud tops, and how warm is the eye in the center of the storm if it's of hurricane intensity. There's a kind of a rules-based approach where you can estimate the intensity of a hurricane fairly accurately within some error bars, and they actually still do this to this day in operational setting. They have both objective and subjective intensity estimates using the Dvorak technique. So there's precedent for infrared brightness temperatures to provide information on the intensity of the storm. So I kind of want to take it one step further and see to what extent can we resolve information about the storm structure, various asymmetries, the tilt of the vortex, things like that. So the way I'm going to be doing it here is introducing this machine learning approach that I'm calling the tropical cyclone synthetic wind analysis using regression models, which is a mouthful. No one wants to say all that. So I'm calling it TC Swarm for short. So what TC Swarm does is it takes a series of initial inputs, characteristics of the infrared brightness temperature field, information about the given grid point is trying to predict distance from the storm center, uses TC environmental characteristics like the vertical wind shear, sea surface temperatures, things that we have in real-time setting. And I also use the best track TC intensity estimate. This information is then fed into a series of upstream machine learning models. One is a random forest model that estimates the vortex tilt of the tropical cyclone, so basically how is the center of the storm leaning with height. And the second model is a gradient boosting regression model that estimates the radius of maximum wind. So this gives us an idea of the spatial scale, the size of the vortex. And then these inputs are used to eventually train the final TC Swarm model that is a gradient boosting regression model that ultimately provides an estimate of the wind field at the given storm relative grid point. So this model is trained on the radial and tangential components of the wind, so I can predict the components of the flow of the TC vortex.
Really quick.
Yes?
So, just so I follow, so you're using like XGBoost to create these derived estimates. They're not really like synthetic OBS?
They're derived estimates. You can, I guess, essentially treat them in some respect as synthetic tail operator observations, because that's what it trained on, is historical TDR observations. I'm going to get there. Does that make sense? Okay. So this model, there's various assumptions that go in. So, I'm assuming that we know the strength of the vortex. That's one of the inputs of best track intensity. I'm assuming we know where the center of the storm is. Again, these are both available in a real-time setting for various official forecast agencies for storms around the world. And so this is a data-driven model. Doesn't know anything about the physics necessarily. So it's learning via this radar database I'm talking about, kinematic structure. And I'm providing it, because it's a gradient boosting regression model, I'm providing it subjectively chosen inputs about the infrared brightness temperature field that I know are related to storm structure intensity and some that I suspect are, and then the model can infer what's useful or not. And so the hope is, right, that the model is going to learn structural relationships like vertical wind shear induced asymmetries of the structure of the storm, and vertical coherence, how tilted the vortex is, things like that. So what is the model trained on? The model is trained on the TC radar database. So the TC radar database stands for the Tropical Cyclone Radar Archive of Doppler Analyses with Recentering. I like acronyms. I helped develop this database. It's basically a collection of all NOAA TDR analyses that were collected over the last 3 decades or so. So we now have upwards of 1,500 unique TDR analyses from over 400 hurricane hunter flights from 1997 to 2024. I'm in the process of adding 2025 once that data is available. And so analyses in TC radar are readily available on storm-centered grids. I impose an objective center finding method I'll talk a little bit about to help find the storm center in these these analyses that have data gaps. And the TC radar database has a wide range of storm sizes and intensities, as illustrated on this figure here. So these are postage stamps of some randomly selected storms. Tangential wind is shown as shading. So you can see we have these very broad and weak systems ranging all the way up to Category 5 hurricanes. Also, the database can be used for 4 easy payments of $19.95. I'm just kidding, it's freely available in .cf format. And so it's posted here in this link. I recently got bored and wanted to try out this whole vibe coding wave and coded up this interactive map. You can go on there and you can parse through the database. You can click on a given storm and look at the various metadata and get an idea of the planned view of the analysis and what it looks like. So if you want to go explore and see what these radar analyses look like, feel free. And now that the sales pitch is done, move on to the model now. So the model is trained on the TC radar analyses, this database of historical TDR analyses. What it's using is, so how are we getting the environmental data? That's taken from the ship's real-time model. This is an operational model that routinely provides forecasters information about the vertical wind shear, the mid-level relative humidity, sea surface temperatures, things like that. So I'm taking information from that. The geostationary satellite imagery I'm taking from NASA's MERGE IR database, which I believe is part of the iMERGE workflow. And so this provides infrared brightness temperatures globally on a 4 kilometer by 4 kilometer grid every 30 minutes, which is really nice. So that way, because we can match the infrared brightness temperature snapshot to the nearest time of the TDR analysis, we get every satellite snapshot within at most 15 kilometers offset from the time of the TDR analysis. Yes?
I don't want to interrupt. This really cool data set. What's the resolution and time of the TDR analysis?
Yeah, I thought I had that in there. I must have glossed over it.
Yeah, sorry.
I was moving some slides around. So these are available on 400 by 400 kilometer grids, so 200 kilometers outward from the storm center. Observations are available, analysis height every 500 meters, from a bottom height of 500 meters all the way up to 18 kilometers in the vertical. So you have 500 meter vertical grid spacing and 2 kilometer horizontal grid spacing. So that depends on the logistics of the flight. Typically, for a given flight, you'll get analysis once every hour for like a total of 3 to 4 analyses, usually. So for each flight, you'll have 3 to 4 different swaths through the center of the storm.
And is that generally thought to be a pretty good, that would be a long time sampling for a deep convection for popcorn convection, but is that pretty good temporal sampling for hurricanes?
Depends on what physical phenomena you're interested in. It's enough you can see pretty quick structural evolution. The problem is you often have 12-hour gaps between flights. And so you can miss a lot in that period. But it's kind of
No, yeah, I get that. That's like the motivation. Yeah, I was just wondering the data when you do have it, like how high in time is it relative to the phenomena of interest?
Yeah, so like over a course of, if you measure rapid intensification over a 24-hour period, usually how it's typically defined, if you have 12 two-a-day flights, you can have like 8 analyses over the course of a 24-hour period.
Are vertical levels, are each aligned to the center? Are they centered, or will the center veer with height?
So the center does veer with height. In this database, I have analyses available in a storm center framework with respect to the low-level center, and I also have another coordinate framework where it's respect to the vortex tilt framework. So you can, depending on what your interests are, you can use either one. Any other questions? Okay, so we're going to use this TC radar database to train our model, TC swarm. And so in this case, so I talked about the inputs here. I interpolate the IR brightness temperatures to the 2-kilometer horizontal grid spacing of TC radar. And I'm using the period 2000 to 2022 as a training period. 2023 is our validation period, and 2024 is our testing period to make sure there's like no data leakage from storm to storm among the groups. And so if you add up each of the data points at like a height of 2 kilometers, for example, this totals 4.6 million training data points, 500,000 validation points, and basically 800,000 testing points. For each analysis, I'm treating each data point as a unique case here. Okay, so I talked about these various components that eventually feed into the final TC swarm model. I just wanted to briefly talk about these, as I think they have kind of unique utility on their own. And so the first I want to focus on is this random forest model that estimates the tilt of the vortex. So first of all, we need to identify what is the tilt of a vortex. And in the TC radar database, we use this weighted circulation maximization technique that I developed that can objectively identify the center of the storm. The idea is basically, if you would look at a map of winds, where would you plot the storm center? It's basically the grid point that best matches idealized vortex of purely cyclonic flow. So kind of like the circulation center of the storm. And you can see in this animation here, this is a case of Hurricane Zeta. We're stepping upward with height as we animate up to a height of 6.5 kilometers. And you can see the vortex is tilted off to the east and then southeast with height, as is in the presence of northwesterly vertical wind shear. So that's acting, the background shear is acting to tilt this vortex over. For the remainder of this, I'm mostly going to be defining vortex tilt as just like this singular displacement in the TC centers at a height of 2 kilometers and in the mid-levels of a height of 6 kilometers. So why do we care about vortex tilt? Well, it turns out that it actually provides of itself very helpful guidance in short-term intensity change. Here's a map of observations. This paper came out in 2024, where on the left panel, we're showing the future 12-hour intensity change. So we have this given TDR analysis. What is the intensity 12 hours from now? The y-axis shows you the magnitude of the vortex tilt, so how displaced are these low and mid-level centers. And the x-axis is this measure of environmental favorability that I call the ventilation proxy. It's defined there. Basically, larger values are associated with less favorable environments or like a greater intrusion of low entropy environmental air into the TC warm core, whereas smaller values are more favorable. So you can see that in the left panel, you see more red dots. Greater rates of intensification occur preferentially in the bottom left portion of the parameter space. So in more favorable environments and in storms that have smaller vortex tilt magnitudes. And if we just partition to just see RI cases on the right, the red dots, we can see again, these occur preferentially in this bottom left portion of this parameter space. And so this suggests that knowledge of the vortex tilt can provide additional information than just this measure of background synoptic scale environmental favorability. So this is pretty useful. So can we estimate vortex tilt just from storm satellite appearance using a random forest model? It turns out we can to within a reasonable extent. I have a couple cases here. The top is a relatively misaligned case. This is what eventually went on to become Tropical Storm Hermine in 2016. And the bottom is a more vertically aligned case, Tropical Storm Ian. You can see that there's pretty apparent differences in infrared brightness temperature field in the left column here, where the misaligned storm has much more asymmetric convective appearance. The aligned storm has a much more symmetric convective appearance. And the right column shows you the machine learning estimate. So the observed mid-level center is kind of tough to see here. The observed mid-level center is shown in the cyan marker, and the machine learning prediction is shown in the magenta marker. You can see that there's overlap in the top right, in the bottom. There's some displacement, but you can also create these probabilistic estimates in the random forest framework, and that's what's shown in that green to red scale shading there. So we can provide an idea of like uncertainty of with the machine learning model's confidence of where the mid-level center is. So in general, we have an RMSE of about 20 to 25 kilometers. If you go back, you can see the range of tilt magnitude. So it provides useful guidance, I would say. And one way, first of all, sorry, I just want to acknowledge some really talented undergraduate students at the University of Miami that helped me refine and develop this model. Will Bouza, Dylan Jarwala, and Matt Reardon. So we're working on a manuscript document in this model. Talking about the utility of the model and these estimates of vortex tilt. Now these are machine learning estimates on the y-axis, and then that same measure of environmental favorability along the x-axis. So even when we don't have TDR observations, the machine learning estimate of the vortex tilt still shows a similar pattern. So the left panel again shows you future intensity change, and the right panel shows you the fraction of all cases within that bin that undergo rapid intensification. So you can see again, preferentially, greater rates of intensification and rapid intensification are realized when the environment is more favorable and the machine learning model estimates that there's a smaller vortex tilt magnitude. For example, in this bottom left panel here, you see here, I don't know if it's right here, you get 37% of all cases in that bin undergo rapid intensification. By definition, R is defined as 5% of all overwater intensity change episodes. And in the top left portion of this same environmental favorability ranking, we get 0 cases that undergo rapid intensification. So this could be a pretty useful kind of discriminant of whether or not, like if you're a forecaster, warning, like this has a high chance of undergoing rapid intensification. Any questions so far? Yes?
When you split up your training, testing, and validation data across the years, and you're using the GOES infrared, you're not using the same GOES satellite across all those years, presumably. So is there any bias introduced because you're using a new instrument that may have slightly different biases?
To some extent, so the Merge IR database does do, I believe, some intercalibration. I don't know what extent they do it from sensor to sensor, but they do parallax correction, and it does have this background consistent 4-kilometer grid spacing. Although in the early period, I believe it may have been a little more coarse. They probably interpolated downward. That is a slight issue, and for really older storms in the database. Yeah.
So your XGBoost is generating a tilt magnitude.
Correct. Yeah. Well, this is a random forest model in this case.
Oh.
That's feeding in the final XGBoost model.
Okay, and then where does the thing that you were talking about having for data assimilation, those were actual radar ops from the aircraft?
Yeah, I'm gonna get there. Yeah, we're gonna create synthetic radar ops. Yeah, so this is
I'm still
this input that builds into the final model.
Got it. Okay.
No, thank you for the questions. Okay. So the purpose of this is these upstream models. This model provides information about the vertical structure of the vortex. This next model is going to provide information about the horizontal structure of the vortex, and then those are going to finally be used to predict the full 3-dimensional wind field. So it turns out these upstream models help improve the accuracy of the final forecast. It's one of the key points here. The last upstream model I'm going to show before we get to the final analysis is a model that estimates the radius of maximum wind, right? So this is the size of the inner core. Basically, we're talking about this really broad hurricane or this really compact inner core. I won't get into all the details of it. This is an XGBoost model. Again, it's trained on the Doppler radar data. It uses infrared brightness temperatures as inputs. We actually developed this derived infrared brightness temperature field that I call the IR vigor, which is to some extent kind of like a time tendency measure that illustrates where you're seeing, to some extent, intense convective bursts that at least where you can resolve from the cirrus canopy from IR imagery. This provided helpful information in identifying the radius of maximum wind. This is just a case of Hurricane Beryl from the test data. And the point is, these analyses are shown every hour, and you can see that there's good stability with time. And it's consistently estimating where the radius of maximum wind is. The cross-validated mean absolute error is about 21 kilometers for all TCs. You can kind of look at this one-to-one plot to get an idea of how accurate is that. So the machine learning prediction radius of maximum wind is shown along the y-axis. The observed radius of maximum wind is shown along the x-axis here. And the left panel just shows shaded by the intensity of the storm. The right panel shows you what is the difference in the azimuth of the average wind at the observed radius of maximum wind and the predicted radius of maximum wind. You say, well, why do you want to show that? Because in really weak storms, what happens is you tend to have these very flat profiles of wind speed. And so your error in the radius of maximum wind could be upwards of 100 kilometers, but it's not really even clear where the radius of maximum wind is because it's just this transient spikes in the wind profile. And so you can see these really dark blue dots here in the right panel. That shows that even it might be far from this one-to-one line, you're not really messing up the wind field, so to speak. So, all errors are equal, but some are more equal than others, maybe. Okay, so this is the last of the upstream models, and that are then used to finally train this ultimate TC swarm model that's going to predict these wind components in the full three-dimensional hurricane vortex structure. Okay, so what is the architecture of TC swarm? Again, this is an XGBoost regression model. It's trained on the storm relative radial wind components, so the wind component moving towards the center of the storm, and the tangential components, so the cyclonic flow about the vortex. I gave it about 100 different predictors, some that are pretty well known to be related to intensity and structure, some that I thought might be useful and just wanted to see what it would do with it. And so this same model is trained on a given analysis height. Like, let's say we're trying to estimate the winds at a height of 2 kilometers. The same model is trained on all data points in the training period on a one point by one point basis. Basically collapse it to this one long one-dimensional list for each variable. And then it iteratively predicts the wind field, reconstructs it on a point-by-point basis. So you could say, Michael, why are you doing this? Why are you using an XGBoost model and not like a neural net or something like that? And there's a couple of reasons for that. First of all, you tend to have these large data gaps in these radar analyses. There's ways you can account for missing data. But also when I started this project, I had like less than 1,000 samples, so I was suspicious how well a neural net would even be able to handle this. So I use an XGBoost model because we're going to party like it's 2014. So let's see. How well does it do? So the left is the observed structure. This is truth. This is the Earth relative horizontal wind speed. The right is the TC swarm estimate. And you can see, it does a pretty good job. Like, it looks like a hurricane. It has an eye with weak winds, an eye wall with stronger winds at a similar radius to what we saw in observations. And the nice part is you get a lot more data coverage, because now we're not limited to the logistics of the flight track. We're not limited to whether or not we have sufficient hydrometeor coverage there. Basically, if we have infrared brightness temperatures and these other information that's consistently available in a real-time setting, we can estimate the hurricane wind field here.
Michael,
So, yes?
is it expected that where you have the observed data, the estimate is different?
So this case knows nothing about reality. So the hope is they would look perfectly the same. Is that what you're asking?
Yeah, they're different. I expected them to be very similar where you have observed structure.
Well, this case doesn't know anything about what the observed structure is for hurricane barrel.
I see.
This is not a case where we're filling in the gaps. I'm going to show that
Okay,
next.
you're generating the full
It knows
okay.
nothing about hurricane barrel. It knows nothing about what the wind field should look like. It knows just what the best track intensity is. It doesn't know what the radius of maximum wind is. It doesn't know what the gale force radii is, things like that.
So you only knows this image in the background.
It only knows that infrared snapshot. Yep. Yes.
I guess I had a question just about the model. You said it's like, again, you said one generates one thing at a time. Is each column independent, or is it like one column feeding into the prediction for the next column, and it's like you're describing an autoregressive?
I'm feeding in like all 100 predictors at once, but it's predicting on a grid point by grid point basis.
Okay, so you could do all the grid points in parallel.
Yes.
Okay, because there is like image generators that do it, like you're saying, one raster at a time using all the previous rasters as inputs. So they can, just wanted to distinguish from that case. Yeah.
So it's the same model, yeah. You could predict it in parallel, yeah. And so Eddie next is going to be talking about like image recognition method of predicting the surface wind field in a hurricane. So he can talk more about it, perhaps a more sophisticated approach.
Is the size okay? It just looks at it. The generated one looks slightly bit smaller than.
So I intentionally kept it on like this 300 by 300 kilometer grid as like a proof of concept. We could go out to the full domain size. We can't go outwards of 200 kilometers because the TC radar database doesn't have data outward of that. And the flight track typically doesn't go more than 200 kilometers from the storm center either. So we're limited by the logistics of the flight track, but I could expand this whole box.
Okay. No, but the storm itself, like.
Oh, the inner core size?
Yeah.
It seems,
Just visually, I'm just like, looks like the observations are slightly larger, maybe not.
typically, the machine learning estimate has a slightly larger radius of maximum wind than in intense storms than reality. It's a little broader. So I do have a more quantitative comparison of the same case right here. Using that infrared snapshot you see on the top left, we're basically trying to recreate this, but with no data gaps. This is the observed case in the middle. The model doesn't know what that is, though, for this case. And this is the machine learning estimate. So the difference plot is shown there on the bottom left now. So you can see in this case, the radius of maximum wind was actually pretty similar between observations and the machine learning estimate. The model tends to underestimate the peak winds in the inner core and slightly overestimate winds in the outer radii. It's kind of like a regression to the mean problem to some extent. You know, the strong winds in the eye wall of a Category 5 hurricane are outlier data points. There's ways you can correct for that, but I won't get into that right now. So if you just look at like a one-to-one plot, so the observed wind field is shown on the y-axis, the TC swarm estimate is shown on the x-axis, we have a correlation of 0.97, which is pretty strong for a case that knows nothing about the observed wind field. And if you just look at like radial profiles of the azimuthally averaged wind speed, you can see that, again, the radius of maximum wind is pretty similar. There's not quite as much azimuthal variability in the range of wind speeds in the machine learning model as we see in reality in this case. And that's kind of a consistent issue with this model. We can look at other cases. So you could say in this case of Hurricane Beryl, you have a well-defined eye. Like maybe it's easy for the machine learning model to know where the radius of maximum wind is and estimate the wind structure. But here's a case of Milton when it just became a hurricane. We don't see any well-defined eye on infrared here. And again, it did a really good job. This is the same kind of 6-panel layout, estimating the wind field. I mean, we have a domain average RMSE of 2.3 meters per second. For reference, the uncertainty with the observations itself is 1.5 meters per second. So for this case, it's like on the order of the observational uncertainty. And again, a good radial profile here. It also, for a given storm intensity, it does a pretty good job capturing relatively small storms versus relatively large storms. So the top is Hurricane Helene. This was a case of a very big storm, had a best track intensity of 120 knots. You can see a pretty broad wind field. And on the bottom is Milton, when it was also 120 knots. And you can see a much more compact vortex. And machine learning estimates reflect that as well, where Milton was much smaller, Helene was much broader. So, one question is, are these analyses or these estimates stable with time? If you get a new infrared snapshot, it's going to predict a totally wildly different structure. And so we can use the case of Hurricane Beryl, which was a well-sampled case, Category 5 hurricane from our testing data set, to look at the stability of the model. And so here's an animation from the same flight you saw before, but now multiple analyses. So this is over a period of about 4 to 5 hours with a snapshot every hour. And you can see at all of these time steps, the TC swarm estimate does a pretty good job falling within the envelope of the observations. And you can see the observations themselves are kind of bouncing around as there's some vortex evolution over the course of the TC life cycle. So I would say, the evolution of the TC swarm analysis is consistent with plausible evolution that we see in these observations. Just to kind of summarize the skill over 2024, the left is a plan view of the composite mean absolute error, and the shading, and the right is the bias, so it's the observed minus the machine learning prediction. So basically, like I said before, the machine learning model kind of underestimates the wind in the inner core, and at least in this testing set, slightly overestimated the winds in the outer core region. We had a domain average RMSE for the full testing set of about 5 meters per second. And 2024 is arguably a pretty challenging case. We had 2 different Category 5 hurricanes in this season, Milton and Beryl. And your RMSE tends to scale. It's proportional to the wind speed as well, at least in this case. So you have weaker storms. It's easier to get a lower RMSE. The median horizontal wind speed error is about 3 meters per second. So just double the observational uncertainty. So I'd argue, in the absence of having an aircraft out there, you could still provide pretty insightful analyses of the vortex structure. Just another way of looking at this, these are just, again, one-to-one plots of the Earth relative zonal component of the wind in the top left, the Earth relative meridional component of the wind, and the Earth relative wind speed for all the cases in the testing database. You can see there's pretty good agreement. And the mean error in the direction of the flow is 8 degrees. So the model is consistently predicting things that look like a hurricane. This is all low levels. We also, I talked about we can do the 3-dimensional structure of the storm. So we're not just looking at the low-level vortex structure. We can then back out what the mid-levels and upper levels look like. So let's look at the estimate of how tilted is a given system. In this case, we're using the case of what eventually became Hurricane Ernesto. It was a well-sampled case. So this is early on in Ernesto's lifetime. The top row shows you analysis at a height of 2 kilometers. So the left panel here, get all the way over here, is the observed infrared brightness temperatures. Here's the observed wind speed at the low levels, and here's a machine learning estimate. Again, it doesn't know anything about the observed wind speed. We see that in this case, it's not even predicting a closed vortex, which is pretty cool. It even sees that it's an open trough at a height of 2 kilometers, which is interesting. And in the bottom row is now showing you the prediction at a height of 6 kilometers, so in the mid-troposphere. And there's like a really misaligned vortex in this case, where the mid-level center is all the way south of like 150 kilometers from the low-level center. And the machine learning model reflected that. So you could say, okay, what if we go forward in time? This case actually aligned with time. Do we see the machine learning model capture this? So we can go 20 hours later, where we happen to have another TDR analysis, and we can see that now on the bottom right, we can see this mid-level center start to slowly shift towards the location of the low-level center. 6 hours later, we can see it move closer. 9 hours after that, and we can actually see this development of this robust mid-level center that eventually becomes aligned at about the same time we see it in observations. So in this case, even if we didn't have aircraft out there, it would suggest that TC Swarm could capture a realistic physical evolution of the full three-dimensional system. At the same time, we saw it more or less with observations here. It did, in the low levels, it was a little too slow in closing off the low-level vortex by about 4 or 5 hours, but I mean, did a pretty decent job, I think. So, this is just a summary of what I just said. What about other physical aspects of tropical cyclone structure? Is it just like predicting this mean state all over the vortex? Are we seeing like asymmetries in the wind field that are related to physical phenomena that we would expect to see? So one of the main drivers of asymmetries in a hurricane is the vertical wind shear. And in this case, this is composites of the full 2024 test case where shear is pointed to the right side. And this is the radial wind. So blue colors show you wind going towards the center of the vortex. Red colors show you wind moving away from the center of the vortex. And we can see pretty good agreement here, where we know in the low levels of a hurricane, we expect to see more inflow in the downshear region of the storm. And we see that from both observations and in the TC Swarm. So it's reproducing physically consistent asymmetries in the wind structure. We even see really cool intercore phenomena. In this case, it actually hinted at picking up on a eyewall replacement cycle in Hurricane Milton. So this is the same kind of 6-panel plot as before, where the blue lines, you can see this secondary maxima in the azimuth average wind. This is a developing secondary eyewall. And you can see the beginnings of this secondary peak in the TC Swarm analysis. It's not quite as pronounced and slightly at a larger radius, but it's still remarkable that just from an infrared brightness temperature snapshot, it can produce a structure like this at a time where we saw it in observations. So, sorry, I had arrows there. So what are kind of some of the remaining challenges? Like I talked about before, the model tends to underestimate peak winds at like really high intensities, category 4 and 5 intensities. I was actively exploring this week, even before the talk, to do, I'm working on a quantile regression model on the side that you can blend the two to kind of pick up on those higher wind speeds and improve the accuracy of the model. Didn't have time to fully implement it, but I think that's an approach that's gonna work. So you can help with this issue. And you can just see that in general, the model tends to have a larger error when you get to higher intensities, which would make sense because you have stronger gradients. So if you misplace where the radius of maximum wind is, you can quickly get really large errors. And if the wind speeds are higher, you can also get large errors as well. The last thing I want to talk about here is that what happens when we do have data? Can we use this model to fill in data gaps? And it turns out that you can by including the case that you have data for in the training data set. Where you're essentially reconstructing the wind field. So this is a case from Hurricane Ivan in 2004 that had a pretty complex intercore wind structure. It actually had 2 eyewalls, so it was undergoing an eyewall replacement cycle. So the top left is observations, and the top right is the reconstruction. So again, the model knows about this case, but it doesn't necessarily know what's going on the outside of that swath for this time. And you can see in the reconstruction, you don't see any sharp discontinuities along the edges of the swath, which is pretty cool. So you see a physically consistent structure that resembles the observations. And if you do like observed minus predicted, the domain RMSE in this case is 0.8 meters per second, which is less than the observational uncertainty. So this seems like a pretty promising tool to, even when you have TDR out there, you can fill in those data gaps potentially. What about weaker storms, where you don't have a well-defined eye? This is a case of, from 2017, Tropical Storm Nate. Look how sparse the observations are in the top left. Like, we have hardly any data. But TC Swarm is saying, well, there's really strong winds on the east side of the vortex. And it knows from the training data that indeed we saw in a past 1 hour later that flew through the eastern part of the storm, there was a really strong asymmetry there. So it can reproduce these really strong asymmetries without these sharp discontinuities on the edges of the swath. And if I actually go back, you can even see the predicted Vmax goes from 31 meters per second up to 34. So it's also reflecting an intensification of the vortex as well. So what do I want to do next? Basically, right now I'm using best track intensity estimates to train and feed the model. It'd be cool if I had a totally independent intensity estimate, something satellite derived. There's already existing products, machine learning products that other groups put out there, but exploring maybe using my own as well, that can kind of separate and make a totally independent analysis from regardless of whatever the operational intensity estimate is. Next thing you talk about is data assimilation. Can we use these TC swarm analyses and treat them as synthetic tail operator analyses to be assimilated in high resolution hurricane models or whatever model you're interested in? And so once I'm actively talking to some colleagues to work on this, once the model's finally refined, that, for a case like Otis, if we had TC swarm analyses before, you fed that into a model like HAFS or WRF or whatever model you want to look at, would you have improved your intensity forecast? And does this information provide things in addition to the all-sky radiances? We'll have to see. And what I think is really cool and what I'm most excited about is with this model, you can theoretically create a high-resolution reanalysis, machine learning reanalysis for vortex structure from the beginning of the MERGER database going back to 2000, if not earlier. And so, this can allow you to do all kinds of things, tackle interesting science questions like what I'm interested in with rapid intensification. How early before the onset of rapid intensification do these unique vortex characteristics emerge? Or, whatever science question you're interested in, secondary eye wall formation or something like that, something that you're looking at the high resolution vortex structure, you can do that with a reanalysis like this. And then you can also train other machine learning models or an emulator, something of that sort, to step forward this synthetic vortex structure in time, and can you make accurate forecasts of TC structure and intensity? So I'm really excited about this possibility. And you could think, well, maybe these IR brightness temperatures, I'm not excited about your RMSE of 5 meters per second. Well, we can also use like I-merge precipitation rates that are available throughout this time too, that I would strongly suspect would improve the accuracy of the model to some extent, where you can look at the convective structure underneath the cirrus canopy. So working on that, and I guess I'm kind of right at time. Here are my key takeaways. I do want to emphasize, I don't think this is meant to replace TDR to any extent. Like those observations are like the gold standard, and the more we fly, the more observations we collect, the better models we can develop. But I think this can be a useful tool that complements that. I do kind of like the hierarchical approach to this model. I found that it improves accuracy by having these upstream machine learning models. And I think, when models are learned on structured representations that map onto known physical concepts like radius of maximum wind, vortex tilt, I think it kind of can improve our confidence in these machine learning models and hopefully the accuracy as well. And in this case, again, we're learning complex physical relationships, asymmetries related to vertical wind shear and things like that, just from a purely data-driven approach. And I'm very excited about the possibility of this high-resolution reanalysis. So if anyone's interested in talking about follow-up work or something, I'm happy to chat more. But again, really grateful for the opportunity to talk to you all today. So thank you.